All right, so this is the lecture for Calculus, section 1.2 out of the textbook for my course. And you can go to my website, which is going to be bmacalculus.net for more information on my course. And the subject for today is exponential functions. And so it's basically y equals n to the x. And we could put some other number out in front here, and we'll talk about that in a little bit. So right now, here I've got a little slider, and so I've got y equals 1.6 to the x, and then I can move that slider and things are going to happen. So the question is, what's going to happen as I increase n? So this is a video where you're going to have your finger on the pause button a lot, because I'm going to be asking a lot of questions and I'm going to want you to think about them before you watch me continue on the video. So what's going to happen as I increase n from 1.6 to say 4? All right, here I go. As I increase it, it gets steeper. So if I increase n, it's going to get steeper. Okay, now the one thing that I want you to notice is that it's pivoting around this point right here. So it's pivoting around the point 0, 1. And if you think about it, it's because if I have 3 to the 0, that's 1. If I have 5 to the 0, that's also 1. If I have 123 to the 0, that's also 1. So any power, any number to the 0th power equals 1. So that means that you're always going to be pivoting around this point right there. All right, so then I guess the next question that I have is what's going to happen. I got to sneak down. What's going to happen when n equals 1? So if I have y equals 1 to the x, what's going to happen? Well, let's see if I can get it. There you go. I've got a straight line. It's because 1 to the 2nd is 1, 1 to the 5th is 1, 1 to the 8th is 1. So I just get a straight line. Now the next question that I have is what's going to happen when I use fractional values of n. So if I say n is 0.5 or n is 0.6 or something like that, what's the graph going to do for fractional values of n? Think about that for a second. And here we go. Boom. So there's n equals 1/2, and so you get y equals 1/2 to the x. So let's look at those. I want to do two functions here. There you go. So I've got y equals 2 to the x and y equals 1/2 to the x. And you see that they are mirror images of each other around the y-axis. And that would suggest, you know, there's some other functions that we're going to be talking about or that you should know about, that if I replace x with negative x, I should get a mirror across the y-axis. These are also known as even functions. This isn't necessarily an even function, but what I'm saying is that here, if I plug in y equals 2 to this one, here I get 1/2 squared is 1/4. And then here, if I go over to the pink one, if I plug in -2, I get 2 to the -2 equals 1/4. That gives me a hint. So let me show you something. Laws of exponents. I can replace 1/2 with 2 to the -1. Same thing. 1/2 and 2 to the -1 are the same thing. Now, if I have a number raised to a power and then that whole thing is raised to a power, what do I do with these two exponents? If you answered you multiply them, then you're correct. So I can actually write this as 2 to the negative x, and I get the same thing. So 1/2 raised to the x and 2 raised to the negative x are the same thing. So here, once again, if I plug in 2 on the pink up here, 2 to the second is 4, and then 2 to the negative second, so let me click up on this one, 2 to the negative second is 2 to the negative 2 is also 4. So this is 2 squared where x is negative 2, and this is 2 squared where x is positive 2. Okay, moving on. I want to give you a very special number before I forget about it, and that number is 2.71828, etc., etc. Doesn't look like much. Why did I choose to pull that number out? 2.718281828. Do you know why I chose that number for special attention? Well, the answer is that is this number e. So if I do e, there I go. E is 2.71828. And e is a very, 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 very important number in calculus, and we're going to use e an awful lot in calculus. So it's best if you understand that number e is 2.718281828, and we're going to use it. We're going to talk about it in a little bit. Okay, I just want to make sure that I get that out there, and believe me, we'll be talking about it later. Okay, so I've got two functions, y equals 2 to the x, and then I've got y equals 2 to the negative x. And then let's start figuring out what we can do with some other functions. So I want to know, what is it going to look like if I do, come on, give it to me. I don't know why I got that text block in there. Okay, so if I do y equals negative 2 to the positive x, what's my blue graph going to look like? So think about that for a second. What is my blue graph going to look like? If you said that it would be the purple graph reflected around the x-axis, you would be right. So here I've got my purple is 2 to the x, my red is 2 to the negative x, my blue is negative 2 to the x, and then guess what the next one's going to be? Negative 2 to the negative x. What's that going to do? That's going to be the reflection of the red. So I've got 2 to the negative x here, and I've got negative 2 to the negative x here. All right, so what I want to do is I want to look at, I want to just sort of jump into what these are good for, and then I will come back and do a sort of a preview of my next lecture, which is 1.3. Okay, so what are these good for? Well, suppose I've got, oh, I didn't do this one yet. Well, yeah, I'm going to get into this. I'll get into this right now. So, I've got a times b to the x minus c plus d. And I want to know what does A do, what does B do, what does C do, and what does D do. Okay, so if you think about it for a little bit, so I want you to think about that for a second, and let's break them down one at a time. Okay. I'm going to look at 2 to the x, y equals 1.5 to the x, and y equals 3 to the x. Okay, what I want you to do is I want you to say that B determines the horizontal stretch. B determines the horizontal stretch. Okay, so as B gets bigger, the stretch gets, the horizontal stretch is less. So this is a B of 1.5, this is a B of 2, this is a B of 3. So as I make B bigger, it gets more compressed or less stretched. So lower B stretches out the graph. Okay? Now let's go back and let's see what's going to happen. Y equals 0.5 times 2 to the x, and y equals 3 times 2, 3 times, times 2 to the x. What's going to happen? Okay. A determines the vertical stretch. More A means more vertical. More A means more vertical stretch. So here I've got an A of 1. If I've got an A less than 1, it's sort of vertically compressed. And if I've got an A of 3, it's vertically stretched. So A determines the vertical stretch. All right, moving in on it. 2 more to go. Let's come back again. Y equals 2 to the x minus 2. What's that going to do? Well, think about it. I bet you can figure it out. Okay, what's happening? X minus, so when a number is subtracted from x, the shift is to the right. When a number is added to x, the shift is to the left. So there's sort of a pattern showing up that what I do to the y, if I'm that more A means more vertical stretch, but then more B means less horizontal stretch, and then a minus C means that I move to higher values, and a positive C and a plus C means that I move to more negative values. So it's almost as if the x's are sort of work backwards and the y's sort of work the way you might think that they would. All right, so then we got one more left to go. Y equals 2 to the x plus 2, and y equals 2 to the x minus 3. And you guys should be able to figure this out. So then when d is positive, the shift is the vertical shift is up. When d is negative, the vertical shift is down. So there's my 2 to the x, there's my 2 to the x plus 2, and there's my 2 to the x minus 3. Okay. And so then what are these good? Let me just do one more to just throw them all in there together. So if I've got 0.6 times, let's just start again. Let's take that out. Y equals 0.6 times 2 to the times, let's do this. This is what I want to do. Y equals 0.6 times 2 times 3 to the x minus 1 plus plus 3 plus 4. Okay, so what's that going to do is it's going to take this function, it's going to vertically compress it, and it's going to horizontally compress it. It's going to move it 1 to the right, and it's going to move it up 4. Okay, so I took it, I moved it, and then, well, I don't know, I won't want to get into the whole, and then I'm lost here. There we go. Okay, so what I did is I horizontally compressed it, I vertically compressed it. Let's do it this way. 0.8. Oh, I've done a whole bunch of things there. Okay, I don't want to get into it. Now I want to tell you what some of these are good for. So I want to give you 3 example problems really quickly. So first example problem is going to be iguanas. Why not iguanas? Okay, so what I'm going to do is I'm going to start with 10 iguanas. That's my A. And then we're going to double every 12 years. So x is going to be my years, and we're going to divide by 12. So when x equals 12, then we've doubled. When x equals 24, we've quadrupled, etc., etc. And so then I back out a little bit so I can see. And I start off with my 10 iguanas. And after 10 years, after 12 years, I'm up to 20 iguanas. And then after 24 years, somewhere right around there, I've got 40 iguanas. And then if I slide it out to 100 years, after 100 years, I've got 3,225 iguanas. And after 120 years, I've got 10,240 iguanas. Okay, so that's probably more iguanas than we can fit on that island. Maybe 10 is a comfortable number, maybe 500 is a comfortable number, but 10,240 is probably not going to be a comfortable number. So there's usually more things going on than exponential growth, and there's Malthus had some things to say about that, and basically exponential growth generally cannot go on forever. Okay, so then exponential growth cannot go on forever, and then everybody sort of thinks that exponential decay can go on forever, but exponential decay can't go on forever either. And so people talk about radioactive decay as if it's just going to go on forever, and it doesn't go on forever. But let me give you a sort of another model of decay, exponential decay, is we're going to do a basketball tournament, and in our basketball tournament, we're going to start off with 64 teams, and then every round we're going to cut it in half. But I could also just say that instead of cutting it in half, we're going to multiply it by 2 to the negative 1 to the negative x. And so then here is my basketball tournament. And when I start off at x equals 0, I've got 64 teams. Okay? Now, it's a little bit weird because it's discrete, but when I go to x equals 1, I've got 32 teams. And then when I go to x equals 2, let me just focus in a little bit more on that. When I go to x equals 2, I've got 16 teams. I go to x equals 3, and I've got 8 teams. I've got 8 teams, and then I go down to 4 teams, and then I go down to 2 teams, and then at 6 rounds, I go down to 1 team. Now, in terms of mathematics, everybody goes, yeah, but it just keeps going out and out and out and out and out. But exponential decay never really works like that in the real world, because if you think about it, you don't in a basketball tournament, you don't keep playing after you have 1 team. You don't go down to half a team, then a quarter of a team, then an eighth of a team, and then a 16th of a team, and then a 32nd of a team. And in the same way with exponential decay, once you get down to 1 atom of uranium, that one atom of uranium doesn't decay into half an atom of uranium and then into a quarter of an atom of uranium. It eventually just decays and then you're out of uranium. All right. So exponential growth, exponential decay, and then I want to give you a terminal velocity one. So terminal velocity, I'm going to give you this. I'm going to say y equals negative, I'm going to say 200 minus 20 to the negative x. Let me see if this works. Let's do this, 1.5. I think I want it this way. That's getting closer. There. Okay, that's what I want to look at. So, this is your terminal velocity. So what happens is, at this point in time right here, you jump out of the plane, and as soon as you jump out of the plane, you start accelerating. And you start accelerating at a really, really fast rate. And as you accelerate, wind resistance becomes more and more. As you go faster, wind resistance becomes more significant, and so there's not as much force pulling you down. There's less net force pulling you down, so you accelerate a little bit slower, but you're still accelerating. And you're still accelerating, but as you're accelerating, the force of friction of the air gets more and more and more, and as the force of friction of the air gets more and more and more, your acceleration continues to slow down and down and down and down and down. And as your acceleration slows down and down and down, you accelerate less and less and less. You just sort of creep up on your terminal velocity, which is around 200 miles per hour. So there's the exponential function that's going to model your velocity towards the ground as you jump out of an airplane and then accelerate up towards 200 miles an hour. But as you accelerate up towards 200 miles an hour, air friction slows that acceleration, so you come up asymptotically on 200 miles an hour. Okay, that's what I want to say in lecture for 1.2, and that is all I have to say.